Lesson 5, Bias Circuits. Section 5.1. Bias Circuit Design. Experiment 5.1. Pause the video, and follow the instructions. The major difference between the circuits in A and B is the resistor Re. At step 4, set the average value V bar Cg at 3 volts by R2. At step 6, heat the transistor using, for example, hot air dryer for about 30 seconds. Although it is difficult to control the temperature with a hair dryer, it allows us to observe the trends in characteristic changes due to heating. These were the waveforms of circuit with the resistor Re in A, before the heating. The average value V bar Cg was set at 3 volts by R2. These were the results after the heating. V bar Cg was reduced to 2.6 volts. These results show that the circuit with Re in A was robust to temperature changes. These were the waveforms of the circuit without the resistor Re in B, before the heating. V bar Cg was also set at 3 volts by R2. After the heating, VCG dropped to the bottom, and the circuit lost amplifying capability. The circuit in B, which did not have Re, was found to be very sensitive to temperature changes. From now on in this section, the bias circuit design will be explained. In this transistor amplifier, VBB and VCC determine the operating point Q. This Q setting is called biasing, and these DC voltages are called bias voltages. This amplifier has 2 batteries for biasing, making it a 2-battery bias circuit. However, a circuit that requires 2 types of batteries is less practical. This is a single battery bias circuit. A circuit that needs only 1 battery is practical. It has 3 additional resistors, R1, R2, and Re, and 2 capacitors, C1 and Ce. The circuit can set the same operating point as the circuit on the left. Let's see how this bias circuit determines the operating point Q. For an analysis on the DC operation of this circuit, let's remove the components related to AC operation. In this circuit, there are 3 DC current paths, I1, IB, and IC. The first step is to determine Re. VEG at the operating point Q is denoted by VEGQ. It is desirable for VEGQ to be approximately 10 to 20% of VCC. In Lesson 3, VCC was 5 volts, ICQ was 0.606 mA, IBQ was 2.85 microamps. Therefore, Re should be within 820 to 1640 ohms. Let's set Re to 1 kilo ohms. VBEQ was 0.66 volts. Thus, VBGQ equals 1.27 volts. Next step is to determine the values of R1 and R2. It is desirable to set I1 is approximately equal to or larger than 10 times IBQ. IBQ was 2.85 microamps. Then, I1 plus IBQ should be approximately equal to or larger than 32 microamps. When VCC equals 5 volts and VBGQ equals 1.27 volts, R1 should be smaller than 120 kilo ohms. Let's set R1 to 51 kilo ohms. Then, I1 is obtained as 70.3 microamps. The reason R1 is not 50 kilo ohms is simply because a 51 kilo ohms resistor is more readily available than a 50 kilo ohms one in Japan. Thus, R2 is 18.1 kilo ohms. This is the designed bias circuit. A variable resistor is used for R2. Exercise 5.1. This is your homework. Pause the video, and answer the problem. The author of this material is Takeshi Furuhashi, Professor Emeritus, Nagoya University. If you have any questions, send emails to this address.